Hi, in this video, I'm going to go through the OCR A-level chemistry paper. This is the Salters specification, and this is paper 2. And I'll just do the first half of this paper in this video and complete the second half in a later one. Okay. Right, aspartame is a dipeptide that's used in an artificial sweetener. The structure of aspartame is shown there. Circle the secondary amide group on the aspartame. Well, the secondary amide is this bit here, yeah, okay. So it's a carbonyl group, an NH group, and the alkyl group stuck onto the nitrogen. Okay, aspartame is hydrolyzed by boiling with acid. One of the products is phenylalanine, which is shown in figure 1.2. Okay, so there's phenylalanine. Phenylalanine has a chiral center. Draw the three-dimensional formula to show the enantiomers of phenylalanine. I'll do it over here on the right. So if you can see which is the asymmetric carbon, it is, the asymmetric one is this one here. That's attached to 4 different groups, okay? So I'm going to put that in the middle there. We're going to have hydrogen, that's in the plane of the paper sticking up. We're going to have the amine group coming out towards us, so that's a wedge. I'm going to have the this CH2 with a phenyl group on it. That's in the plane of the paper as well. And then I'm going to have a carboxylic acid group that's going back into the plane of the paper there. Okay, so we're going to draw the mirror image of that. There is our imaginary mirror. And all we've got to draw is the reflection of that. So we want the carboxylic acid going into the plane of the paper there, the amine coming out, the phenyl group, CH2 phenyl group here, and then the hydrogen at the top there. So there's the 2 enantiomers, the 2 non-superimposable mirror images of phenylalanine there. Okay. Right, phenylalanine exists in solution mainly as the zwitterine. Complete the diagram to show the structure of the zwitterine. Right, so I've drawn the structure as a non-skeletal here. Sometimes it's easy to get confused going straight to skeletal. Okay, so that is this is going to be the that carbon there, the carbonyl carbon. So we need to have that, and in the that's not the carbonyl carbon. This is what's confusing. Right, let's number the carbons here. We've got 1, 2, 3. Okay, so there is 3, 2, 1. So that bond there, that is going to the O minus. That's the carbonyl. And on number 2, we are going to have the protonated NH3 group, the NH2, which has got protons stuck to it. Okay, so there is our that is the zwitterine. Okay, the zwitterine, the carboxylic acid is ionized and also to give a negative ion, and the amine group is also ionized to give the positive group, 2 charges on the ion. Okay, a student says that acid hydrolysis of aspartame will only produce phenylalanine and 1 other amino acid. Comment on the accuracy of the station. Okay, then that isn't right. Now let's have a look at this diagram here. We can see, give the structure of any compounds you write. Right, we have got a peptide bond here. Okay, so we're going to break that peptide there. But if you look here, we have also got an ester linkage, right? So we've got an ester linkage there. That is also going to be broken. That will be hydrolyzed. So what we're going to get then is we're going to get this thing, which is aspartic acid, all this stuff here. Okay, so I'll draw that. So that's one of the amino acids. And the right, so that is now, I'll draw it like that, not in the zwitterine form, I'll just draw it normally. Then we've got phenylalanine, which I'll do, which is all that stuff there. So I'll just copy that as it's drawn. So that's going to be an NH2 group, a free NH2 group, not NH anymore. It's been hydrolyzed. And we've got the carboxylic acid, right? Now, this is not going to be the ester as it is here. See there, it's an ester. It's going to be a carboxylic acid. So that means we're also going to make methanol. You see there, that is the alcohol, CH3OH. Okay, so that's the 3 compounds we're going to get there. Okay, aspartame tastes sweet. One theory is the sweetness is caused by hydrogen bonds forming between sweetener molecules and sweetness receptors in the body. On the structure of aspartame, circle all the atoms that could hydrogen bond with the receptor. Right, so what do we need for a hydrogen bond? We need oxygen, nitrogen, or fluorine, and we need a hydrogen attached to that. So that hydrogen can hydrogen bond. And the forms of hydrogen bond too, either oxygen, nitrogen, or fluorine with a lone pair on it. Okay. So the hydrogen bond is the interaction between this delta positive hydrogen and the lone pair on ON or F. We haven't got any fluorines to worry about, so you can forget about that. But this oxygen has got lone pairs, so that could form hydrogen bonds. This hydrogen, well, that's attached to an oxygen, so it's very delta positive, so that can. The oxygen it's attached to has got lone pairs, so that can do it. This oxygen has got lone pairs, that can form hydrogen bonds. This hydrogen attached to nitrogen, so it's very delta positive. The nitrogen has got a lone pair on it itself, so that can. The same with this nitrogen, it's got a lone pair, and these hydrogens, again, that oxygen, and then this oxygen has also got 2 lone pairs. So loads of atoms that can form hydrogen bonds, one part of a hydrogen bond, potentially. Okay, the enzyme pepsin catalyzes the hydrolysis of protein chains. Some students read that the pepsin breaks the peptide bonds adjacent to aromatic amino acids. So that's like, for example, phenylalanine, things with a benzene ring in it. This is because the active site is specific to benzene rings. Okay, so a benzene ring is that. Now, what kind of intermolecular forces? So there's a benzene ring, which is attached to the phenylalanine. Type of bonds that form between a benzene ring and the active site. Well, benzene ring has got no polar molecules. It can't form hydrogen bonds. It can't form any dipole, permanent dipole-dipole interactions. So it's got to be London forces. In other words, temporary dipole-dipole interactions. The student mixes excess aspartame. This is important for the next bit of the question. The fact they've got excess substrate in aqueous solution at room temperature. After 30 minutes, they place a spot of the mixture on some chromatography paper. Describe the rest of the method, including how they could tell whether hydrolysis has occurred. Okay, and you may include a diagram. I think I will. It's easier to explain it with a diagram. So what we need to do is we need to get the piece of chromatography paper with our spot on it. And this is the start line, which should be drawn in pencil so it doesn't dissolve in the solvent. The piece of paper is then placed into a container, containing a beaker or something like that, with solvent in it. Okay, and you have to be careful the solvent is below the level of the start line and the spot. Okay, and then you usually put a lid on that to stop the solvent evaporating. Okay, otherwise, if it's a volatile solvent, it will be gone before you have a chance to do the chromatography. Okay, how can you tell whether the hydrolysis has occurred? Well, you take the paper out afterwards, and you won't be able to see anything on the paper because amino acids are white and colorless, and you can't see them. So you need, there's a start line. You need to spray with ninhydrin, which will react with amino acids to form colored spots. Alternatively, you can look at it under UV light because most amino acids will absorb UV. And how can you tell whether hydrolysis has occurred? Well, if hydrolysis has occurred, you're going to get more than one spot. You've split it up into at least two different things. Okay. And so that we account for all 4 marks there. Now this next bit, having excess aspartame, that is important for the next part of the question. Okay. Other students boil the mixture of aspartame and pepsin to attempt to speed up the hydrolysis reaction. Okay, explain whether or not this would work. Of course, it wouldn't work. No, because you would denature the enzyme, and it wouldn't work anymore. The enzyme would stop working. This bit is important. Another student says using a higher concentration of aspartame. Well, in the method, it already says it is in excess. Okay, so if it's in excess already, increasing the concentration of it is not going to speed up the reactions because, well, you don't need, all you need to say is because enzyme catalyzed reactions are 0 order when the substrate is in excess. And the reason for that is because the enzymes, where the substrate is in excess, all the enzyme active sites are kind of like occupied and carrying out catalysis, and they carry out catalysis, then another one goes into position. So having lots more excess aspartame isn't going to make it any faster. The only way you can make it faster is by having more active sites there. In other words, having more, increasing the concentration of the enzyme. But all you need to say is that there. Okay, this is about electrochemical cells. Students use a method based on electrochemical cells to measure the concentration of silver ions in solution. They set the cell up like that. There's something missing. Describe what it is. Well, it's obviously a salt bridge. Okay, and what is a salt bridge? Well, it's a piece of, usually it's a piece of filter paper soaked in a saturated solution of really any ionic compound, but here wouldn't be a good idea to use chloride or something because you've got silver ions there. So commonly potassium nitrate is used. That would be fine. 2 marks. That's all you need to say there. Okay, 2 conditions necessary for the cell to measure electropotential under standard conditions. Right, so you want all ions to be at a concentration of 1 mole per decimeter cubed. And there's no gases involved here, so I won't say standard, I won't say, 1 atmosphere pressure. I'd say instead I'd say 298 Kelvin. Okay, should be the temperature. Okay, so we've got the electropotential data for the cell. Equation shows the reaction occurs when the standard cell delivers a current. Okay, so identify the oxidizing agent. Okay, so well, it is actually silver as the oxidizing agent. How do we know that? Well, the oxidizing agent gets reduced and the silver goes from a +1 oxidation state to a 0. That's one way of looking at it. The other way of looking at it is, well, let's have a look. What happens here is the silver, that goes forward, so it's taking in electrons, and it's going to remove the electrons from from the copper. It's going to go backwards, that reaction. So it's taking electrons away from the copper, so it is oxidizing the copper. But you don't have to explain it, you just need to identify it. Ag+ is the answer. Right, state and explain which way electrons flow in the wire when the standard cell is delivering a current. Okay, so here I've done this. So again, this is the most positive, so that is going to go take in the electrons and go forwards. And that's most negative, that's going to give away the electrons. So the copper's giving away the electrons, so they're going to be going around that way, from left to right in our diagram. Put the salt bridge in there. Okay, so the electrons will go from left to right. Explain why. Well, the silver ions are taking electrons away from the copper metal. Okay, silver bromide is usually described as insoluble, but a small amount, of course, will always dissolve. The students have a saturated solution of AgBr, which will be very dilute, Okay, it contains as much AgBr as will dissolve, and they place that in the right-hand beaker, the cell. Okay, so we're going to put that here. So this will not be under standard conditions. We're going to have very low concentrations of silver ions. All right, now, okay. They measure the cell potential, and the result is 0.09 volts, okay, with the same polarity as in standard cell B. The students are told the relationship between the measured potential is given by this, okay? So we need to, they've told us what E cell is, they've told us in this case it's 0.09 volts. We need to know what E standard is, okay? So we need to look at this table. So E standard is going to be equal to the E right minus the E left. The E right standard value is E cell right there. The E right is the silver one, that's 0.8, and the left hand is the copper, so that's minus 0.34 volts, which is equal to 0.46 volts. Okay. So we've got E value here, so we know that this is 0.46. We've got to calculate the silver ion concentration, so we need to rearrange that equation. Right, let's get the here. Let's get the so I'm going to starting off with this equation here. All right, first thing I'm going to do is I'm going to subtract E standard cell from each side of the equation. So we're going to end up with 0.06 log silver is equal to E cell minus the E standard cell. Right, let's put the numbers in there. So we get 0.06 log Ag plus is what was E cell? E cell is 0.46. Sorry, 0.09, they measured it. 0.09 minus E standard cell, that's 0.46. Okay, so divide by 0.6, both sides of the equation, we get log Ag plus is equal to 0.09 minus 0.46 divided by 0.06. So log Ag plus is equal to, that works out to be minus 6.16. Now we're going to get rid of that log, so that means that Ag concentration, Ag plus concentration is equal to anti-log 10 to the power of minus 6.16. Put that into your calculator, you get a value of 6.81 times 10 to the minus 7, and the units of concentration are going to be mole per decimeter cubed. So that is our answer there for 4 marks. Right, some students make another cell using 2 different half cells. Okay, so we've got the 2 half cells there. Write an equation for the reaction that occurs when the cell delivers current. So look at these 2 values. Which is the most positive? It's this one. So that is going to draw in the negative electrons. If it's positive, it's going to pull in negative electrons. So that means this one is going to go forwards. And this is the most negative one. So this one is going to go backwards, giving away 2 electrons. But the bottom one uses up 10 electrons. The top one only gives out 2. So we're going to have to multiply that by 5 before we add them together. So let's do that. So we are going to get 5 copper is going to react with 2 iodates, 12 protons, and that is going to give us 5 copper 2 plus ions, I2, and 6 waters. That is our balanced equation. Okay, state symbol is not necessary, I don't think. Right, that's that one there. Draw a label diagram to show how the iodate I2 electrode is made up, and you don't need to give concentration, so we need a beaker. Okay, now we need a mixture of the oxidizing and the reducing agent. So both everything present in this equation we're going to need in our everything we're going to need. So we're going to need iodate ions, H plus ions, iodine, and don't worry about the water. So we've got in there, and it says we don't need to tell you so what the concentration, I2, hydrogen ions from sulfuric acid or something, and some iodate ions. Now you'll need something to form electrical connection there because we haven't got a metal there. So the standard thing to use is platinum. So that's what it will be. That will be our cell, our half cell. Okay. Right. The students are told that in a standard iodate electrode, the iodate concentration squared is equal to the iodine concentration. They plan to prepare 40 centimeters cubed of the solution of the electrode by mixing 20 centimeters cubed of 0.08. Now that's going to go up to a total value of 40. 20 goes to a total value of 40. So the final concentration of iodine is going to be half that because you diluted it. Yeah. So that's going to be 0.04. So what is the final concentration of iodate that we need? Well, here we've got iodate is equal to iodine. So iodate concentration final is going to be equal to the square root of 0.04, which works out to be 0.2 mole per decimeter cubed. That is not the end of the story. That's the final concentration of the iodate. So what strength of the solution do we need for the 20 centimeters cubed of the iodate? We need to know what, well, it's obviously going to have to be double that, isn't it? Because you're adding 20 of that and then you're diluting it to 40. So the concentration of the iodate solution should be 0.4 mole per decimeter cubed. Right, now I think that I'm going to have to now change my whiteboard because, okay, so I will see you on the other side. It will go funny for a minute. Okay, so we're back. Let's just get me to the top of this. Right, the next question. Right. Okay, so we've got this potassium hydrogen phosphate is added to fertilizers, and it acts as a buffer, and it also supplies phosphorus. Okay, the H2PO4 minus ion has two OH groups. Draw a dot cross diagram for this. Well, if you remember what is phosphoric acid, which is obviously comes from this. Phosphoric acid is like this. Unionized phosphoric acid. Phosphorus is in group 5 of the periodic table, so it quite often forms 5 bonds. As you can see, it is forming there. It's allowed to have more than 8 in its outer shell because remember it's in period 3, so it's the third shell being filled up, which is, so you've got, it's not just 8 electrons because you've got 3s, 2 electrons in there, 3p, you've got 6 electrons, and you've got 3d, because you've got room for a lot more electrons. Okay, so let's draw what's that going to look like. So we're going to have our phosphorus there. Right. And we have got 4 oxygens. Okay. Right. There's our phosphorus. And these are our oxygens. It's got 2 OH groups. So let's draw the H's. I'll draw them there. Okay, so this oxygen at the top, that's going to be a double bond. So I'm going to do dot across and dot and across. Let's say that, so the crosses, I've drawn 2 crosses from oxygen. There's 6 in the outer shell of oxygen in group 6. So I need 2 lone pairs there. This is going to be a single bond, so that's going to be a dot and a cross. This is a single bond, a dot and a cross, and this is a single bond, a dot and a cross. Right, now that is a cross from the oxygen. It's also a cross from the oxygen. That is an electron from the hydrogen, that red one. So that's all the hydrogen electrons accounted for. Now these oxygens, they're both in group 6, these two on the left here, and I've only drawn 2 electrons so far, so I need to do 2 more lone pairs, one there, and here. Right, here's our oxygen. Right, the oxygen we need to draw on this one. Well, it's got 6 electrons, so we need to draw 5 more. 1, 2, 3, 4, 5. And then we've got another electron here, which has been taken somewhere else, and that's why it's got this negative charge. That would be our dot cross diagram for that ion. I suppose it's important to know the structure of phosphoric acid before you start trying to do that, and it's probably useful to know the dot cross for phosphoric acid and for sulfuric acid as well. It's always useful. Okay. So this KH2PO4, when used in fertilizers, is equivalent to adding 50% of phosphorus 5 oxide and 34% potassium oxide by mass. They use as fertilizers. Show the mole ratio for potassium to phosphorus in this mixture is the same as in that. Now, what is the mole ratio in that? Let's do first of all. Well, look, from the formula there, we can say we have 1 mole of potassium to 1 mole of phosphorus. It's a 1-to-1 ratio. So we need to try and show that we've got a 1-to-1 ratio of potassium and phosphorus moles in that mixture. Let's do that. Right. Useful. Let's get the MR of P2O5 first of all. MR of P2O5, phosphorus is 31, oxygen is 16, so that gives us 142. And let's get the MR of potassium, a different color maybe, of potassium oxide. Potassium is 39.1, oxygen is 16, so that gives us 94.2 for that. Okay, so let's say in 100 grams of this mixture, we're going to have 52 grams of phosphorus P2O5. What's the moles of that? So the moles of P2O5 is equal to mass over MR. The mass is 52, the MR is 142, so that is going to give us 0.352. Right. Now, how many moles of phosphorus have we got? Well, 1 mole of P2O5 obviously contains 2 moles of phosphorus, so we need to double that. So moles of phosphorus is equal to 2 times 0.352, which is equal to 0.704 moles. That's the moles of phosphorus. Let's now do the moles of potassium. So in 100 grams of the mixture, let's try and do it in a different color. In 100 grams of the mixture, we're going to have 34 grams of potassium oxide. So the moles of K2O is equal to going to be mass over MR. So that's 34 over the MR of that, which we said is 94.2, which is equal to 0.361. So we've got that moles of potassium oxide. Again, we've got 2 moles of potassium for every 1 mole of potassium oxide. So moles of K, we're going to double that. 2 times 0.361, which is equal to 0.722. Now you can see there, look, so here's the ratio of the moles then. We've got 0.704 moles of that to 0.722 moles of that. They're approximately the same. So it is a 1-to-1 molar ratio, which is what we had in the compound here. Right. So here we have the H2PO4 minus ion is acting as a weak acid, isn't it? Right, it's giving away an H plus. Right, so I'll just answer that question really. Look, this is the proton donor. This is the acid. As the reaction goes backwards, that thing is acting as the base because that reacts with an H plus ion. So the base is HP4 2 minus, and why is it? It is a proton acceptor. When the reaction goes backwards, calculate pKa for the equilibrium there. Well, pKa is simply equal to the minus log of Ka. So that's the minus log of the value they give us there, 6.2 times 10 to the minus 8, which gives us a value of 7.2, and whatever you want, it's 2 dp, okay? 7.2. Right. Now, what we're going to do is we're going to calculate the pH of a 1 times 10 to the minus 3 mole solution of KH2PO4. Now, this is behaving as this is behaving as an acid. So let's call that HA. This is its conjugate base. So let's call that A minus. Okay. Save us writing out the formula. Now we know the expression. Right. So let's go over here. Let's do it here. So we know that Ka for a weak acid is equal to H plus concentration multiplied by the concentration of the conjugate base, A minus it, and HA. So I'm going to write down the equation here. We've got HA, and that's going to dissociate to give us A minus and H plus. So I'm going to put down here start concentration, and here equilibrium concentration. So the start concentration is before any of this thing has had a chance to lose a proton, and they tell us that is 1 times 10 to the minus 3, isn't it? So that's 0.0001. Now the start concentration of A minus, its conjugate base, none of it's dissociated, so that's going to be 0. The H plus concentration, well, it won't really be 0 because a little bit in the water, but we can ignore that because it's going to be much more dilute. So we'll call that 0 as well. Now let's say at equilibrium, let's say X of that is dissociated. So we've got 0.01 minus X, the concentration is dropped. So that means the concentration of A minus must be X and the concentration of H plus must be X. We're going to put these, now we'll do a little cheat here as well. This is a weak acid. It's weak acid. So that means X is very, very small. It's much smaller than 0.01. So that 0.001 minus X is approximately equal to 0.001. We always do that. That means we'll avoid having a quadratic equation. Okay, so we've got to put the numbers into this equation here. Okay, let's do that. So we get Ka. They tell us it's 6.2 times 10 to the minus 8. Is equal to X squared over HA, which is 0.001. Let's rearrange that. X squared is equal to 0.001 times 6.2 times to the minus 8. So X squared is equal to 6.2 times 10 to the minus, multiply that out, that should be minus 8 there, not 3. That's to the minus 11. Okay, and we need to take the square root of that now to find X. I'll have to go over here, sorry. So X is equal to the square root of 6.2 times 10 to the minus 11, which is equal to 7.87 times 10 to the minus 6 moles per decimeter cubed. Right, let's not lose sight of the fact that X is the concentration of H plus ions. So H plus is equal to 7.87 times 10 to the minus 6. Let's take a negative log of that to get a pH. Minus log of that is equal to 5.1. Yeah, 5.10. So that is the pH of our solution, a dilute solution of KH2PO4. Right. Now, the acidity of this of the H2PO4 minus ion reduces the loss of ammonia from ammonium ions. Explain how this happens when a fertilizer is in solution. Okay, when you have NH4, it is a weak acid itself, and it's in equilibrium with NH3 in aqueous solution and H plus. And okay, so what will happen if you get NH3 in aqueous solution? It's a gas, and it can evaporate, and you'll lose it. Right. So if you add some acid, okay, so add acid, you're going to be adding H plus. Le Chatelier tells us what's that going to do to the position of that equilibrium? It's going to push it to the right. Okay, so the equilibrium moves to the right. In other words, you've got less NH3. Okay, so you're not going to lose that as gas. You've got it as the NH4 plus ion. Okay, a mixture of HPO42 minus. Now that is going to be like A minus, I'm going to call that. Okay, that's the conjugate base. And this, which is its conjugate weak acid, in solution make a buffer. Okay, of course, a buffer is a mixture always of a weak acid and its conjugate base. So that's what we've got here. Okay, so calculate the mass of KH2PO4 that must be added, right? So that is going to contain the weak acid. Okay, that must be added to this, which is the weak base, to make a solution with a pH of 6.5. Okay, so whenever doing a buffer calculation, it's always a good idea to start off by writing down H, rearrange your Ka expression so that you get, Ka is equal to H plus over A minus times A minus concentration divided by HA. So if you rearrange that, you'll get H plus is equal to Ka HA over A minus. Right. Let's see what we do know here then. Okay. So, all right, what I'm going to do first of all is I'm going to substitute. See this concentration of HA and A minus. And so HA concentration in the buffer is equal to moles of HA divided by the volume of the buffer V. The V is actually 1 dm cubed here. All right, but it says the volume doesn't change, and we'll see later it actually does change, but it doesn't make any difference. They're trying to make it easy for you, but it won't make any difference to the calculation anyway. So HA is equal to moles HA over that, and the concentration of A minus, of course, is going to be moles of A minus over V. So let's substitute those green values into that equation on the left then. So what do we get? We get H plus is equal to Ka multiplied by moles HA over V divided by moles A minus over V. What's going to happen to those V's? They're going to cancel out. So that's why we don't need to know the volume. If the volume increases a bit when you add a bit of solid, it doesn't make any difference. Okay, so let's put the numbers in there. Well, what do we know? Do we know the moles of HA? No, we don't. That's what we've got to find out. Okay. But we do know the moles of A minus, because look here, let's put this down. We add 1 dm cubed of a 0.1 molar solution. So the moles of A minus is equal to the original conc of A minus times by the volume. The original concentration is 0.1 and the volume is 1 dm cubed, 1. So that's going to be 0.1. Okay. So Ka, we know they told us Ka earlier is equal to, what was it? It was 6.2 times 10 to the minus 8. So I'm going to, so H and H plus, well, the only thing we don't know here is moles A minus, is moles HA, and that's what we've got to find out. So I'm going to rearrange that equation. Moles HA, right, is going to be equal to H plus concentration divided by Ka multiplied by moles of A minus. And we know all of those, so, right. H plus, well, the pH is 6.5, so H plus is equal to 10 to the power of minus 6.5, isn't it? So that's going to be equal to 10 to the power of minus 6.5 divided by Ka, which is 6.8 times 10 to the 6.2 times 10 to the minus 8. The moles A minus, we've just worked that out, is 0.1. So we evaluate that, what do we get? That is the moles of HA is equal to 0.51. Now we need to work out the mass of HA, the mass of HA, which is potassium hydrogen phosphate, okay, dihydrogen phosphate. So the mass of that is equal to moles times MR. The MR of that stuff is, you add that up, 39.1 for the potassium, 2 for the hydrogen, 31 for the phosphorus, 4 times 16, that gives you 136.1. So the mass is equal to the moles, which is 0.51, multiplied by the MR, 136.1, which gives us 69.4 grams. Okay, now if you put 69.4 grams of solid into just 1 dm cubed of water, there'd be a fairly significant change in volume there, where they said there wasn't, but as we've seen, because those volumes cancel out, it doesn't make any difference to the calculation. That is our correct final answer. And I think that is about halfway in the paper. It's not quite, no, there's a little bit more here before we finish the video. Right. A student says that a solution of HPO42 minus alone will act as a buffer when acid is added. The student says this because the position of equilibrium moves to the left to remove H plus ions. Well, just we've almost answered that question. It's a strange question, really. Will it act as a buffer? Yes. Why? If you add H plus, it's going to tend to remove H plus by pushing the equilibrium that way. Okay, so I'll say that. I think you also need to say until all of the HPO42 minus is used up. It will only act as a buffer as long as you still got some of that left. As soon as that's all used up, then it will stop buffering. Okay, now a student is doing calculations involving solutions of hydrochloric acid. The student says that the concentration of hydrogen ions can be taken as the concentration of the acid. Well, that's usually okay to say that. For 1 mark, if you look at the mark scheme, yes. Why? Because HCl is a strong acid and it completely dissociates. So 1 mole of HCl gives 1 mole of H plus ions. That's all you need to say there. Now, the actual answer in the mark scheme for this next bit is definitely wrong, okay? Right, I'll tell you the way they do it and what they say, and I'll tell you what the real answer is significantly different to what they say. Right, okay, calculate the change in pH when 1 drop of HCl is added to 1 dm cubed of water at pH 7. Okay, so what we're going to do is we're going to do the moles of HCl added. That's going to be conc times volume which is 0.01 times 0.05 divided by 1,000. And that gives us a value of a very small number, 5 times 10 to the minus 7. Okay, now what they say in the mark scheme now is that you should do, so what we should do is we should say the new H plus ion concentration, call that new, is equal to the moles of H plus divided by the new volume. Now the V volume is 1,000 centimeters cubed, 1 dm cubed plus that little bit. Well, we can ignore that, that's fine, and they've ignored that, which I agree with, that's fine. So that gives us 5 times 10 to the minus 7 divided by 1. So the new concentration is 5 times 10 to the minus 7. So how do we find the pH? So pH is minus log of that. Which is equal to 6.3. Okay. And so the pH change, they'll say there is going to be 7 minus 6.3 is equal to 0.7 of a pH unit. Right, that is actually quite a bit wrong. Okay. And the key to this, it says in the mark scheme, it doesn't, right, the key to this is that's a very small number of extra hydrogen ions. I'm going to call them extra because we've already got some hydrogen ions in the water. Okay, so H plus ions in the H2O. Right, normally we ignore that because it's tiny. It's 1 times 10 to the minus 7 mole per decimeter cubed. Which is much smaller, but here it's actually approaching, you know, it is not much smaller at all. It's of the same order of magnitude as that one there. So that's the extra ones that added. So we've got in 1 dm cubed of water, how many moles of H plus have we got? That's 1 times 10 to the minus 7 moles. So now I'm going to do the total moles of H plus. So that's the H plus extra plus H plus from the water. The H plus extra is 5 times 10 to the minus 7. From the water, we've got 1 times 10 to the minus 7. So that gives us 6 times 10 to the minus 7 moles. So what's the concentration of H plus? Well, that's in 1 dm cubed. So the new H plus concentration is equal to 6 times 10 to the minus 7 mole per decimeter cubed. So the pH, take the minus log of that. That gives us 6.22, which is like significantly different to their answer there. Right. Anyway, if you did the in blue, you got the marks anyway. Right, that is the halfway through the paper, and so I will do the next in the next video, the next half in the next video.